Hello. In this lecture, we will continue last week's theme and talk about paired testing, but this time for data that is not normally distributed. Last week, we talked about how to compare two independent samples with a continuous outcome variable. We had a population 1, and we were interested in comparing its mean to a population 2 by only observing a sample from population 1 and a sample from population 2. Based on these two samples, we ask, is there a difference in the mean of population 1 and population 2? Or is the observed difference in the samples due to chance? We use this to introduce key terms in statistical hypothesis testing. For example, the null hypothesis. The null hypothesis in this scenario states that there's no difference between the means of the two samples. The alternative hypothesis is that there is a difference. Remember, this situation is not symmetric. While the null hypothesis is a point hypothesis, which posits that the two means are exactly equal between the two populations, the alternative hypothesis encompasses a range of options, including many different possible scenarios on exactly how the two populations can have different means. We then defined our test statistic. The test statistic measures how well the data agrees with the null hypothesis. Namely, in this case, the scenario that the two populations are not different in their means. We also needed a way to compute the so-called null distribution. That is, the distribution of the test statistic under the assumption that the null hypothesis is true. We use this null distribution to compute a p-value. And we defined the p-value as the probability of observing data with a test statistic as or more extreme in magnitude than the observed data. This is also shown in this graph again. This is the null hypothesis, a null distribution of the t-test. And for each data set, we observe a test statistic. And we compute the p-value as this shaded blue area under the curve. This is the probability of observing under this null distribution a test statistic as or more extreme than the one that was observed in the data. Adding these two blue areas on both sides gives us a p-value. If the p-value is sufficiently small, we take this as evidence that the observed difference between the two sample means is large enough that it likely does not come from two populations with the same means. One of the key assumptions of the t-test that we covered in the last video was that the data follows a normal distribution. If you don't remember all the details of the t-test, please watch the last video again. So what do we do if we encounter a scenario like this? So here we have an hypothetical example with a data set where the data is non-normally distributed. You can see that these data points here in this sample are all very close together, while here some of them are close together and some are really spaced far apart. You will remember from one of our first lectures a way to diagnose whether data is normally distributed or not. The so-called quantile plots or QQ plots. Here, we plot the corresponding theoretical normal scores against the data points. If the data is on a straight line, this tells us the data is close to a normal distribution. The data is clearly not on a straight line. This tells us that our data does not come from a normal distribution. So if we fit by eye two straight lines to these data sets, then we observe quite some differences. So these points here in the tails are not well captured by a straight line. So likely our data that I've just shown you does not come from a normal distribution. So if we want to compare the two sample means statistically and test the hypothesis whether the two populations have the same mean, then we need something else because the assumption of the t-test is violated. In this case, we use the so-called Wilcoxon-Mann Whitney test, or Wilcoxon rank sum test. This test does not assume a normal distribution, but it tests a very similar null hypothesis as the t-test. The null hypothesis in this case is the populations from which the samples were drawn have the same distribution of soil respiration. And the alternative hypothesis is the distribution of soil respiration rates tend to be higher in one of the two populations. Of course, this is already adapted to our example, but you can imagine how this can be phrased more generally. The Wilcoxon-Mann Whitney test has a test statistic which is called U, and it measures the degree of shift between the two samples. To this end, we simply count for each sample in one of the two, for each data point in one of the two samples, how many data points in the other sample are smaller than it. And then we sum all these values up, and we take the smaller of the two or the larger of the two, depending on which book you look into. Let's look at an example illustrating some of the extreme scenarios that we can obtain. So for example, here sample 1 is entirely shifted to lower values than sample 2. So all of the data points in sample 1 are smaller than the data points in sample 2. So we compute two values, K1 and K2. And in K1, for K1, we simply count for sample 1 which of the data points in sample 2 are smaller than it. We start with the first data point, and we observe that none of the samples of sample 2 is smaller than it. We do that for all the points in sample 1, and because it's entirely shifted to the left, none of the data points has a value larger than 0, and when we sum them all up, we obtain exactly 0 as the total for K1. We compute another number, K2, which is the same statistic for sample 2. So we ask how many data points in the sample are smaller than the first point in sample 2. The answer is 5, because all of the data points in sample 1 are smaller than the smallest data point in sample 2. So here's the first data point of sample 2, and here are the 5 data points in sample 1 that are smaller than it. And we obtain exactly the same value of 5 for all the 4 points in sample 2. When we sum these values up, we obtain K2 equals 20. And in fact, the maximum K that you can get in a Mann-Whitney U-test is always the number of samples in sample 1 times the number of samples in sample 2 in such an extreme scenario. If the two samples are reversed on the x-axis, then of course also the numbers are reversed. From this, we calculate the test statistic U by taking the maximum of these two numbers. And this measures the degree to which the two samples are shifted towards each other. We can see that by looking at another situation where the data points are exactly interleaved. So one data point is smaller than the second sample in sample 1. Two data points in sample 2 are smaller than the third sample in sample 1. 3 data points are smaller than the fourth sample in sample 1. And 4 data points are smaller than the fifth sample in sample 1. So that means we obtain a test statistic K of 0 plus 1 plus 2 plus 3 plus 4. And this is 10. When we do the same game for the second sample and go through all the data points, we also obtain 10. Taking the maximum returns a test statistic for the Wilcoxon-Mann Whitney test of 10. Now, what do we do with this test statistic? Again, one can mathematically compute the null distribution. The distribution that we obtain if the data adheres to the null hypothesis. So under the assumption that the null hypothesis is true, we compute the distribution of both the K and the U scores. And then we can judge again how likely it is to observe the observed value of the test statistic under this distribution. So the distribution for K1 and K2 is symmetric. And now, when we take the maximum, then it's of course not symmetric anymore, because then the smallest number is 10 and the largest number is 20. Let's look at the example again of this soil respiration rate in the growth and the gap condition. We saw that this data is not normally distributed, and so we want to apply the Wilcoxon-Mann Whitney test. So here we have a table of all the data values. So here is the first data set, the growth data set. Here's the second data set, the gap data set. So for each point in the growth data set, we here count how many points in the gap data set are smaller than it. So the first value in the growth data set is 17. And we observe that exactly 5 values in the gap data set are smaller than 17. For the second point in the growth data set, which is 20, we find that 6 data points in the gap data set are smaller than it. And so on and so forth for all of them. We can then look at it the other way around and compute the number of observations in the growth data set which are smaller than any of the points in the gap data set. And we find, for example, for this first point here, that none of them are smaller. This continues until we reach the 18, and this is larger than the 17. So here's an entry of 1. Then, to compute our case, we sum all these values up, and we obtain a K1 of 49.5 and a K2 of 6.5. We compute the test statistic U by taking the maximum of these two values, which is clearly 49.5. In the case of the test, to convert this to a p-value, we can, for example, look it up in a table, in a book, or use statistical software to do so. So we can see that a U of 49.5 for a sample of size 8 and 7 will yield a p-value that is between 0.014 and 0.009. So in this case, this is smaller than 0.05. So we would conclude that this data provides sufficient evidence to reject the null hypothesis. So we would conclude that the mean of the growth data is really significantly higher than the mean of the gap data. So how does this test compare to a t-test? Why do we not always use the Wilcoxon-Mann Whitney test if it makes less assumption and tests the exact same scenario? So the Wilcoxon-Mann Whitney test does the trick of not having to assume a normal distribution by working on the ranks. The ranks are the relative orders of all the data points. So for the Wilcoxon-Mann Whitney test, it doesn't matter how much larger a certain point is. It just matters that it's larger. So you just need to know the relative order of the data points to compute it. Therefore, it's called distribution-free. So it does not make any distributional assumptions to compute its null distribution. For the t-test, we assume that the data in both samples comes from a normal distribution. And this helps us compute the statistic, the test statistic under the null hypothesis or the null distribution. And we can show analytically that the form of that null distribution for the t-test is a student's t-distribution. The problem with the Wilcoxon-Mann Whitney test is that it has less power if the t-test is applicable. To remind you what power is the probability, or the probability of finding a difference if there really is one. Or 1 minus power is our type 2 error, namely of concluding that there is no difference or finding not enough evidence for a difference if really there is one. So this is why we often use the t-test. Because we make more assumptions, we have more power to detect deviations from the null hypothesis. If your distributions are highly skewed, so if they have very long tails, for example, then the Wilcoxon-Mann Whitney test actually has more power. In spirit, it is actually relatively similar to a randomization test, and you would typically report it with a median and, for example, confidence intervals of the median. With this, I thank you for your attention today, and have a nice day.